Okay, so welcome back to the second of my lectures on implementations of parallel programming models. What I talked about last time was this imperative programming model. It was a data-centric programming model that I said is very useful for what we call irregular programs. So these are programs that deal with large graph data structures. And one of the things that I would like you to think about in the background is, well, there are many programming models. So, for example, one could use functional languages for doing that kind of parallel programming. Think about some of the algorithms that I gave you and ask yourself how you would implement those in Haskell or some other functional language. So I think it's useful, even if you're interested in functional languages, to understand how other people do business. Because after all, most of the people doing parallel programming in the world are not doing it using functional languages. They're doing it using imperative languages. So if nothing else, you need to know what the rest of the world is doing. So I think that's one thing that I'd like you to keep in mind. Now, the other thing that I want to do, and this is what I'm going to focus on today, is to tell you how to think about implementing parallel programming models. And the particular material I'm going to cover today has nothing to do with our data-centric model. It's an introduction to parallel architectures and also to some low-level programming models. So in particular, something called pthreads and MPI, which are used to program shared memory and distributed memory machines. And even if you're interested only in Haskell and nothing else, well, ultimately, you do need to worry about these concerns. And so unless you're a pure Joe and you say, well, I just want to stay very naive about architectures and so on, and I don't really care what happens if my performance is bad, well, okay, I'll just call some Stephanie somewhere and hopefully she can fix my program for me. Unless you're operating at that level of abstraction, the things I'm going to talk about today are of concern to you, regardless of which programming model you implement, because they really have to do with the basics of parallel architectures and how one writes these low-level programs for these architectures. So my talk is going to be somewhat different in style from Bob Harper's. So I've known Bob for many years, of course, and I'm always amazed that he can give entire lectures purely on the blackboard, just consulting a whiteboard, consulting his notes. So I'm going to be using slides as before, in particular because I want to show you a bunch of graphs, performance graphs, things like that. Okay, so I'm going to call this lecture a programmer's view of shared and distributed memory architectures. And I'm going to tell you about how to think about shared memory and distributed memory architectures for parallelism as we go along. But this is not a lecture on low-level architectural details. Rather, it's about what do you need to know about these kinds of architectures in order to be able to write programs that perform well, right? So we're going to be dealing with these architectures at a somewhat higher level of abstraction than you would see in, say, a computer architecture course. So here's an overview of shared and distributed memory architectures. So if you've never come across these terms before, so shared memory architectures, so here is one example of a shared memory architecture that's very popular. So Intel's latest latest processor chip is called Skylake. And so you can buy a chip from them that has up to 18 cores. So each core is essentially like a CPU, it's like a computer, and you can be running programs on each of those cores and exploit parallelism. The key point is that all of these cores can be connected. This chip can be connected to some common memory. And so the way you program a chip like this is you take your application program and then you decompose it into a bunch of threads. So each thread is basically like a single program. These threads are all operating in parallel. Each thread gets executed by one of these cores. And because all of these cores are sharing the same memory, these threads can communicate with each other by simply reading and writing out of common memory locations. So in my pthreads program, some of the programs I'm going to show you, I can declare a global variable x, and then different threads can write to x, read from x, and so on, and communicate in that way. Another thing you can do, and this is actually quite common, you don't use just one chip, you use multiple Skylake chips, for example, but it's a relatively small number of them that you connect up together and you build a shared memory machine out of them. So there are various low-level programming models where you explicitly deal with parallelism in order to program shared memory machines. And these systems are called, these are libraries. So pthreads is a library. And then Intel has something called OpenMP and threaded building blocks that are layered on top. I don't have the time to talk about all of these, so I'm just going to focus on pthreads and try and give you some idea about how to write pthreads programs and also how to understand performance of pthreads programs. And the way to think about this is, even if you're a Haskell programmer, if you're doing parallel computing with Haskell, ultimately these are the kind of concerns. So in fact, a compiler could take a Haskell program and translate it down into a pthreads program, for example. Okay, the other kind of machine is the classical machine, the old-style parallel computing, if you will, which is still very relevant, of course, and that's distributed memory. So here, what you do is you build a network of machines where each machine is one of these shared memory machines. And so at the Texas Advanced Computer Center, for example, we have the Stampede 2 machine. So it's a large cluster, and it's got 4,200 of these Knights Landing machines from Intel. So there are 4,200 of these, and then each one of these Knights Landing machines has about 300 cores within it. And so you can see you get an enormous amount of parallelism. The key difference between shared memory and distributed memory is that these machines don't have any memory in common. So each machine has its own memory. The cores that are on that machine can read and write, communicate through those, but if one machine wants to communicate with another machine, you have to do it very differently. You have to do it by message passing. So you have to send a message which has to be received at the other end. In addition, data structures also have to be partitioned between the different processes, between the different machines, because there's no common structure, no common memory. So if I have a large array, what I have to do is partition that array between the different machines. And then you have to do all the communication of values and so on. So there's a standard, a library, which is called MPI, Message Passing Interface, that became standardized in the mid-90s, and today everybody uses MPI. And so I'm going to show you a couple of MPI programs just to give you an idea of what's involved in writing MPI programs. Okay, so one analogy for shared and distributed memory is, at some level, this room is a shared memory interaction, right? Because if you want to communicate with me, well, all you do is you raise your hand and then you talk and everybody else gets to hear it and so on, right? So we're like a big, well, not a very big, but we're like a shared memory machine, right? So each of us is a core and we can communicate with each other because I can see what you're doing and so on. If, on the other hand, I'm doing this in an online way, so I'm sitting in my pajamas in my hotel room or something and giving this lecture, and each of you guys is in your own, you're at Starbucks and you're sitting somewhere else and so on, well, then the mode of communication obviously has to be very different. So if you have a question, well, you can't exactly raise your hand and hope to get a response from me. What you might do is to instant message me or send me email. You would send me a message, right? So it's a very different style of interaction. So then that would be more like a distributed memory machine. Okay, any questions about this? So I encourage you to ask questions. I realize that the kind of concerns that we're going to be talking about here are very different from the concerns that Bob and others have addressed. And so if you have any questions, please feel free to raise your hand in this shared memory environment, and I'll do my best to answer your question. Okay. So let's start with shared memory architectures. And again, I want to show you how to think about shared memory architectures from a programming point of view. As we said in the previous lecture, parallelism used to be a concern only for computational scientists who were using clusters and so on. That was the old style parallelism. But today, as we talked about, your cell phones, all of your laptops, all of these are little parallel computers. They're little shared memory machines, in fact. The question is, well, what made this change from old style to new style? Why is parallel hardware now ubiquitous? Right, as opposed to just being confined to some clusters in large-scale supercomputing centers. So anybody have a quick answer to that? Does the question make sense? What happened in semiconductor technology, processor design, and so on, that all of a sudden we have multi-cores everywhere, right? We have trouble increasing clock speeds. That's right. Okay, and we have trouble increasing clock speeds. Why?
Because heating thin and then things just break down.
Things just melt, essentially. That's right. Okay. So why were we in the past, why were we able to increase clock speeds? Each new generation, the clock speed got faster. So here, on the x-axis, this is time, right? And on the y-axis, there are numbers. And to interpret that number, you have to look at the color of the line and see what's going on over here. So here's the frequency. So this is the frequency that we were talking about. And as you can see, the frequency increased exponentially, but then it flattened out around 2000. Right? So this is what you were talking about. And it flattened out essentially because of power considerations. Okay, your chip started to melt if you clocked it any faster. Okay, so why were we able to increase the frequency over here? That's basically because with each successive generation of transistor, the transistors got smaller. And because they got smaller, it took less time for them to switch, to communicate between transistors and so on, so you could increase the clock frequency. But the key point is that the transistors, each transistor got smaller, right, by a factor of 2. So what that said is, for a given chip size, you doubled the number of transistors in every generation. Okay, and this is called Moore's Law, right? So it's named after Gordon Moore, who was one of the founders of Intel. And back, I think, in the early 70s, he wrote a paper which basically said the way processor designs, computer chips, are going, with each new generation, you get twice as many transistors. And so somebody decided to call this Moore's Law. And so Moore's Law basically says you'll always have more, right? And you can see Moore's Law over here, and you can see Moore's Law is still continuing, right? You're still doubling the number of transistors. However, each of these cores is not being clocked any faster. So what do you do with all these additional transistors? So what people have done is they've built these multi-core processors. So this black line over here, as you can see, shows you the number of cores on a single computer chip, like the one we were talking about. So it was 1 all along, and then all of a sudden, starting in the mid-2000s, you can see now we have between 10 and 100 of these cores all sitting on the same chip, right? So that's where multi-cores come from. So basically, your transistors, they continue to get smaller. Moore's Law continues to hold. And what we're doing with these additional transistors is building these additional processors on the same chip. Okay, so here is sort of a block diagram of this Intel Skylake chip that I was telling you about. So this is a Skylake multi-core chip that has 4 cores on it. Okay, so there are 4 CPUs. Each one is capable of executing 1 thread of computation, so 1 little program in your overall program. And as you can see, they all share what's called the last level cache. So there are multiple levels of cache. The last level cache over here is a L3 cache, as it's called. L1 and L2 are the higher levels of cache. Okay, if I look within each one of these blocks and I open it up, I'll see something like this. And this looks horribly complicated, but basically there are 3 parts. There's a front end of the core. What the front end does is it's responsible for fetching and decoding instructions. So there's a program counter, and you start fetching instructions and decoding them and so on. The execution engine over here, that's where all of the ALUs are. So floating point addition and multiplication and integer operations, vector units. So they're all sitting over here. And then you have the memory system. So you have the L1 data cache, L2 data cache. This is connecting to the shared level 3 cache. And then you can attach this to memory. And so this part is connected with attaching to memory. So does it make sense, essentially? So you have these 4 cores. Each core has its own program counter. It has its own registers. It has its own L1 and L2 caches. However, these 4 guys share the same L3 cache. And then you can put a bunch of these guys together, a bunch of these chips together with some memory attached to each one of these chips. And then that gives you a shared memory machine. Question? Make sense? Okay, so at this point, you're probably looking at all of this and saying, geez, that is really complicated. Do I really need to understand all of that in order to write shared memory programs for these shared memory multiprocessors? Well, if you think about it, this is actually the block diagram of a single core. So even if you're writing a sequential program, well, do you have to deal with all of that complexity? No, you obviously don't. So how do you hide that complexity? How is that complexity hidden from you? Can you write a program for that single core without knowing anything about the details? Yes. So what is it called? It's called a compiler. And the compiler generates what? Well, every processor has an instruction set architecture, which is called an ISA. So these are just the instruction set of the processors. And so as long as you know how to write those instructions and put them together for a program, then in principle, you don't need to deal with all of that complexity. So that's this abstraction layer that's being provided by the architects. It's a contract made between the software and the hardware that if you write these programs in this machine language, right, or assembly language, you can think about executing each one of those one instruction at a time. And the hardware guys guarantee no matter what tricks they do underneath, the program result that you will get is the same as ignoring all of that complexity and just thinking about executing one instruction at a time. Okay? All right. So we're going to do the same thing for multi-cores. So what I want to show you are 3 concerns that you need to have when you're writing these shared memory programs. And if you address these 3 concerns, then in some sense, the hardware guys take care of the rest of it. Okay? And these 3 concerns are called cache coherence, atomic instructions, and the memory consistency model of the processor. So how many of you guys know something about cache coherence? Okay, raise your hands a little higher. So, okay, so that's about half the class. How many of you know atomic instructions? Oh, a lot more. Okay, well, that's interesting. Okay, so I'm going to cover each of those in a little bit of detail because I think roughly half the class doesn't know about these things, and that's just fine. So I'm going to show you a bunch of cartoon pictures and so on in order to explain these basic concepts. So cache coherence essentially has something to do with the interaction between caching and program semantics. So what it says essentially is unless you worry about something that's called coherence, the fact that you have caches in your cores may change the semantics of the program. And that's very different from what we do for sequential programming. For sequential programming, you know, you can essentially ignore caches if all you're interested in is the semantics. Caches are there for performance, but the result of executing your program on a machine with a cache is the same as what it would produce if there was no cache. So caches are invisible to the software in single-threaded sequential programs. And what I'll show you is, unless you worry about something that's called cache coherence, and it's a very simple idea, the fact that there are caches may change the meaning of your program, and so you do need to worry about it, and I'll explain that to you. Atomic instructions essentially mediate interactions between threads. Since these threads are all executing in parallel, every once in a while you need to make sure that they're coordinated, right? So they don't step on each other. So this is called synchronization, and atomic instructions are a way of implementing this synchronization between cores. The memory consistency model is a very tricky thing. This has something to do with the fact that each core is reordering instructions. It's executing instructions out of order. Again, if you're just writing single-threaded programs, that's completely invisible to you. You just get better performance, but it doesn't change the semantics of the program. It turns out in a parallel program, a shared memory program like the ones that we're going to write, this kind of reordering, if you're not aware of it and handle it properly, it may actually change the semantics of the program, which is very strange, but turns out to be true. So that's called a memory consistency model. Now, for lack of time, I'm not going to talk about the memory consistency model. That's a very deep topic. So we're going to ignore this, and I'm just going to focus on getting you to understand cache coherence, how to implement or how to think about cache coherence, atomic instructions, what's involved with atomic instructions, and then how those are used by the pthreads library. Right? So I'm going to show you some implementations of various constructs in pthreads that use these ideas. And then you can use pthreads to do whatever you want. So does that game plan sound reasonable? So we're starting with this hardware-software contract, essentially, and getting that straight. So think of it as an extension of the ISA. The ISA is a software-hardware contract that the hardware guys say, well, as long as you write to this model, I'm going to implement it very efficiently for you, but you don't need to worry about how I do it. If you worry about these three issues, you get the same kind of benefit, same kind of abstraction, but for shared memory programs. Question?
In instruction reordering, it's specific to the compiler, right? So the performance being the compiler reorders the instruction, right? And for every compiler, it's going to be different.
Okay, so that's a good question. The question is the binding time of the reordering. Who is doing the reordering? And these reorderings, as you're pointing out, can be done by the compiler, right? So I have two assignment statements. The compiler may decide to do them in a different order, right? Because you can prove that these commute. But this reordering that I'm talking about is actually being done by the processor. When it's executing these instructions, even though we think about instruction execution as one instruction at a time, it turns out that for efficiency, the instructions themselves can be done out of order by all of that hardware that I showed you over there. So the memory consistency model is something that you need to worry about at the language level. So you need to tell the compiler if there are issues over there. And in addition, you need to be aware of the memory consistency model of the processor. So in other words, what kind of flips of these instructions and commands and so on is the compiler going to do? What kind of changes is the architecture going to do? And you need to be aware of that. But as I said, for the programs that I'm going to show you, we don't need to worry about it. So for now, I would suggest not worrying about it. I'll be happy to talk to you later. Yeah? Yeah, later meeting at lunchtime. Right, not in this lecture. Yeah.
Would you consider speculative execution as part of the memory consistency model? Or that, because it obviously violates architecture of software contrast.
It could do that, that's right. So, yeah, that's right. So all of that you'll have to worry about in there. That's correct. But again, we're not going to worry about it because for the programs that I want to show you and I want you to be comfortable with, we don't need to worry about that. So we just worry about cache coherence, atomic instructions. If you guys come out of this saying, oh, this is easy stuff, I know how to do it, we'll declare victory, and then over lunch, I'll be happy to talk about memory consistency models. Good, all right. So let's start with the cache coherence problem. And again, just to define what this problem is, as we said, when you're just talking about a single-threaded machine, a sequential core which has some cache and so on and so forth, the fact that there is a cache is invisible to the software. Your software, your program will just run faster because if you get a lot of hits in your cache, well, then the memory accesses appear to be, in fact, they are faster. However, it doesn't change the semantics of your program. So I'm going to assume that you know at least that much about caches. I'm going to consider very simple multi-core architectures where there are 3 cores, there's only one level of cache. The argument I'm going to make is easily extended to multiple levels of cache. And again, I'm not going to talk about it here, but if you're interested, we'll do lunch. So we can have a very busy lunch. We need to have a long lunch, that's right. But fortunately, Zaina has scheduled a long lunch for us. So, yeah. So, okay, so you get the idea. So there is a core. Each core has just a single level of cache. And then there's this shared memory over here. I'm going to assume there's just some variable x that all of them want to read and write into. Okay, so here's a sequence of operations that might happen. So the first thing is, at some point, core 1 says, oh, you know what, I want to read the value of x. So it issues that address into the cache, it misses in the cache, so then it does what's called a bus transaction. So in other words, it pushes out that address on the bus and says, I want to read from this particular line. So then that particular line gets copied into the cache over here, and I'm just going to show it as materializing there, okay? For now, I'm going to assume that this cache line just has x in it. Later, we'll worry about the fact that this cache line may be longer than just, for example, if x is an int, 32 bits, but the cache line might be 64 bits, so it might actually bring in some additional stuff. For now, don't worry about it. We'll just assume the cache line has x, and x comes in there. Okay. The next thing is cache 2 loads x. Same thing happens over there, right? It misses in the cache, it goes to memory, it says, please give me a copy of that. So now a copy is there. Okay, now core 1 says, I want to write 32 into x. So what's going to happen there? You update x, but which x? The copy in the core, right? So again, the core issues that address into the cache. It says, hit. I got a cache hit. Oh, this is wonderful. I don't need to go out and worry the bus and so on and so forth. I'm just going to update it to 32. Okay, and now let's say that core 3 wants to read the value of x. So it is in the cache, and it says, okay, I need the value of x. And now all of a sudden the question is, what do we mean by x now, right? Because memory and core 2 think that the value of x is 24, whereas core 1 thinks the value is 32. So should we give it 32? Should we give it 24? Should we add the two values and say it's 56, subtract them? What should we do, right? This is the cache coherence problem. In other words, if your caches are not aware that there are other caches in your shared memory system, then all of a sudden what looked like a single variable, right, namely x, the abstraction that caches provide you in sequential programming is you can ignore the cache when you're writing your program. It's just as though there is one location called x. All of a sudden, everybody has a copy of x, and they're all writing into it and reading from it and so on. This is insane. Somehow we need to control what's going on over here so that we retain that illusion that there is only one thing called x. So that's cache coherence. Okay, question.
So once core 1 updates the value of x, it will push the value in the shared memory, right? Because it's writing the value of x.
Okay, that depends upon whether you have a write back or a write through cache. So if you have a write through cache, which is what you're talking about, anytime a core updates a cache line, it also does a bus cycle and updates it in memory. But if you have a write back cache, then it's only when this line gets evicted from the cache, right, to make room for some other cache line, that's when you go and write it in there. But notice that even if I had a write through cache, right, what would happen? 32, so then memory would get updated to 32, but it's still the case 2 and core 1 sort of disagree about what x is. One guy thinks it's 24, the other guy thinks it's 32. Memory is, depending upon whether it's write back or write through, agrees with 1 or 2. This is chaos, right? And it's basically happening because it's like, having a sign-up sheet where I have multiple copies of a sign-up sheet and I just hand it out to all of you guys and everybody starts filling in the sign-up sheet. And well, okay, that doesn't really make any sense, right? We need to control this kind of sharing that's going on. And that's the essence of the cache coherence problem. Okay. Questions? Is this clear? So basically, when you have caches and you have a multi-core processor, each cache needs to be aware that there are other caches in the system. That's what we're saying. Another question is, what does it mean for them to be aware? That's what I'm going to tell you about. You still don't look convinced. You're not convinced. All right. Boy, you're tough. All right.
I'm not sure how it's
No, each cache design, right? You basically, all caches nowadays are write back. So just assume write back. It doesn't matter whether it's write back or write through, but all caches today are write back caches. Because that reduces the number of bus cycles you do, right? The bus is a shared resource between all the cores. If every time you write to something in cache, even if you get a hit, you want to go and update memory, that's going to cause a lot of bus traffic. So you can see it's better to write back only when you evict that line. Okay? Good.
So once shared memory is updated,
Yeah.
its value will not be updated in all the cores which are using that value?
Yeah, because right now, these cores are not aware of each other's existence, right? When you do a bus cycle, all that's happening is you're updating the shared memory or you're reading from the shared memory, right? But you're not aware of the other caches. Okay, so as long as you ask the question, now give me a solution. What is the simplest solution you can imagine to avoiding this problem? So in other words, a solution to the cache coherence problem. So let's go back to the sign-up sheet. So instead of making a lot of copies and having chaos because all of you are signing up for the same slot and so on, what should I do? There should be only, get rid of, okay, good. So that's one solution. Cache coherence is a problem, get rid of the cache. But what's going to happen? What's going to happen is even your sequential programs now are going to be slowed down dramatically just because you might be executing, okay, Intel will, well, it's already in trouble, but it'll be even more trouble if, this is the solution that they adopt. So we're going to reject that solution. So what should I do with my sign-up sheet? Well, there should really be only one sign-up sheet. So that's the first thing. And then if somebody wants to sign up, well, then that sign-up sheet should be forwarded to that person and so on. So can we implement something like that here? So what's the basic idea? The basic idea is one way to solve this problem is we can ensure that a given line, in this case a given variable, x, is cached in at most one cache at a time. It may not be cached anywhere, but we'll ensure if it is in any cache, is there in exactly one cache. And if anybody wants it, any other cache, any other core wants it, it needs to get it from the core that owns it. So intuitively, there's only one sign-up sheet, and then that has to be passed around between you guys if you want to sign up for it, right? That's the idea. Okay, so how would you do that? Well, one way of doing that is what's called a Snoopy cache, right? You know the word snoop? Snoop basically means to spy on something. So you take advantage of the fact that this bus is a shared hardware structure, and whenever a core wants to get something from memory, say write to memory or read from memory or whatever, it's going to put that address out on that bus. And so all the other caches can look at that address and say, oh, is this an address that I have in my cache? And if so, they can step in and take some action, right, in order to ensure coherence. So how would I ensure that there's only at most one copy of X if I have Snoopy caches? So Snoopy caches just say, I'm going to look at the reads and writes, and if this is a read or a write to a line that I have, I'm going to step in and make sure that things don't get out of hand. Okay, so give me the protocol. Sorry?
Eject it if you see it, when you have it. So we already have a cache, throw it out or something.
Okay, so let's go back to this situation over here. So at this point, core 1 has X, so it's cached over there. Now we said core 2 wants to load X. So it's going to put that address on this bus. This guy can snoop on that and say, oh, you know what, X, I'm going to do something. So what should core 1 do? You should forward it. So in other words, we're going to do cache-to-cache transfers. And what should really happen, I don't have a cartoon for this, but basically this line will be sent over to cache 2 because cache 1 can see that address and says, no, don't go to memory, I'm going to give it to you. So that's a cache-to-cache transfer. So that gets over there. Now when core 1 stores 32, what's going to happen? It's gotten rid of it from its own cache. So this is said to be an invalidation. It's invalidated it from its own cache. It's now in 2. So then when it goes to access it on the bus, 2 steps in and says, no, I have it. So I'm going to give it to you. So then this line will come back over here. This will get updated to 32 and so on. Okay? So if I do a load or a store and I get a cache hit, I don't need to do anything. I know I have the only copy of it, and I can just go and update it or read it right away. If, on the other hand, I get a miss, I put that address out on the bus. If any other cache has it, it steps in and forwards that line to you. Okay, that's a trivial idea. Okay, it's also not a very great idea because it turns out what this does is, sorry, is there a question? Yes?
I was going to ask if the cache-to-cache transfer caused a lot of latency because it forces like taking a thread or a core away from what it was currently doing.
No, because it turns out this is all done in hardware. The core doesn't need to be involved in it. Okay, there's just hardware sitting over there that takes care of the core-to-core transfers. Okay, so I'm going to call this exclusive caching. It's a word that I just made up when I was preparing this lecture, but nobody really implements it. They implement a version of this. Why don't they implement this? Well, they don't implement this because in some sense this exclusive caching is too draconian. It's too strict because it prevents cores from sharing even read-only data. Right? There's a cache line, let's say a table of constants. Nobody is writing to that table of constants, but even then, right, we're going to prevent a given line from being stored in multiple caches. So this is the protocol that's actually followed. It's called a write-invalidate protocol. And basically, it's like this exclusive caching that I was telling you about, but a line can reside in multiple caches if everybody is just reading from that line. So I have that line in my cache because I just read it from memory. If you also want to read it, I'll just forward it to you, but I don't invalidate it in my own cache because we're all just reading from it. But if any cache wants to write to that line, it does that bus cycle, invalidates it from all other caches, and then it gets to write. So that's why it's called write-invalidate. Okay? And then there is an implementation of this that's called the messy protocol. And the messy protocol is basically what is implemented. But if you understand what I was talking about with exclusive caching, and then this particular write-invalidate twist on it, well, then you basically understand what I need you to take away. Are we good? Okay. All right. So one thing that you've already noticed is that if core 1 and core 2, if both of them are writing to X, this is called, first of all, true sharing. And when you have true sharing, this cache line is going to do what? It's going to bounce back and forth between the caches. Because we said to write, you have to have exclusive access to it. So if you and I are both writing to this cache line, it's going to go back and forth. And this is called ping-ponging. So it's a technical term that's used to say, if you have true sharing, two or more cores are writing to the same line, well, then it goes back and forth like that between the different caches. And that obviously reduces performance because you have a lot of these invalidation misses. Every time you write, it gets invalidated in my cache, right? Okay. Now, there is a more pernicious problem that might occur, and this is called false sharing. So what is false sharing? Well, again, let's go back to that cache line which was beginning in memory. This time, I'll assume that CPU 0 only writes to X, CPU 1 only writes to Y. So there's no true sharing, right? They're interested in different variables. They're reading and writing from different variables. Unfortunately, they just happen to be on the same cache line. And we said the unit of transfer is a cache line. So what's going to happen over here? If 0 and 1 keep hammering on X and Y, oh, you know what? For that, I have an animation. So first you get that, and then you get that. When this guy does the write, it goes back. Now you can see why it's called ping-ponging. It's like this game of ping-pong or table tennis, right? This goes back and forth, lots of invalidation misses. Performance will be terrible. You may think invalidation misses, okay, it's not, well, turns out it can basically kill all of your performance, and I'll show you some numbers. Okay, so to summarize cache coherence, basically the solution is you use Snoopy caches and a write-invalidate protocol. Each cache has to be aware that there are other caches in the system, and you just take action to ensure that you have exclusive access to a cache line when you write to it. True sharing is when two or more cores are writing and reading from the same variable or array element. False sharing is when there are two of these locations that just happen to be on the same line. Well, you still have this ping-ponging going on. So this reduces performance, and to improve performance, you have to try and reduce the sharing of cache lines between the cores. Okay, are we good?
This burden of reducing sharing between the cache lines is on the programmer.
On the programmer, that's right. The hardware can't help you. you need, this is how caches are implemented on these multi-core processors. You need to make sure you don't have fault. If you can reduce true sharing also, well then so much the better. And in fact, that's the example that I'll show you when I go to pthreads, which I need to get to quickly. Okay, we're happy over here? Yeah, go ahead.
How do registers come into play here? Are they sort of considered as part of the cache? 'Cause
No,
there's gonna be some-
they're just separate.
Okay, 'cause you could load up a cache and have.
Yeah, you can load off a cache, then it'll be in a register, but then it has nothing to do with the memory system at all. Right, if you remember that big picture, right, there was the front end, there were the execution units. The execution units have all the registers sitting over there. It's nothing to do with the memory system. That's between you, you're a core, that's between you and your registers and your ALUs and so on. Memory system doesn't care. Okay? All right. Okay, the only other hardware idea that I want you to know about is what are called atomic instructions. Okay, and this again is a feature of multi-core processors. You don't need to worry about atomic instructions in single-threaded programs, multi-threaded programs. You do need to worry about it. So I'll motivate atomic instructions by using this very simple example. Let's say there's an array. There are 2 cores. You just want to sum up all the elements in the array. So a simple way of writing a parallel program is core 0 adds up all the elements in the first half of the array. Core 2 or core 1 adds up the second half of the array. Okay, so now I have a value, you have a value, which is my contribution and your contribution to this global sum. So can I just go ahead and add my value to sum? There's a global variable sum. We said that is shared between all the cores. Can I just add my value and your value by just doing x equal, or sum equals sum plus v, and you do sum equals sum plus v also?
No.
Okay, why not?
I would load, and you would load that we will add to the same old value.
We may add to the same old value. So unless you and I make sure that our additions are done in sequence, right, what's going to happen is we may both add to the old value. In fact, what may happen is in some runs of the program, we may add to the old value and get the wrong answer. In other runs of the program, maybe you're slower than I, okay, let me be polite. I'm slower than you are, and so you go ahead, you do your addition, and then I come along and then I do my addition, and then everything looks okay. So depending upon which execution you're talking about, you get different answers. Oh, gee, that's terrible, right? I mean, you guys hate non-determinism, I know, I can tell from the last few days. Well, this is called a data race, right? A data race is basically a race between all these reads and writes that are going on to the same variable. You need to coordinate the actions of the different cores to make sure that there are no data races in the program. Okay, so this was for a single variable. The general problem is there is a data structure, right? An array or a struct or whatever you guys call it, and you want to go and atomically update all of those elements. But we'll just worry about a single int at a time, right now. Okay, so here is an illustration of a data race. So when I was first studying this stuff a long time ago, somehow it never made sense to me because it just seemed like, well, I just add my value and you get to add your value, and why can't that happen, you know? Okay, so the reason that doesn't happen atomically, in other words, as though it was happening instantaneously, is you have to say, if this guy is doing x gets x plus 1, how is that actually implemented in the instruction set, right, in the program? Well, the way it's implemented is this gets translated by the compiler into something that looks like this. It says load from address x into the value into register 1, so your register over there. So load from x into register 1, increment register 1, so I'm just adding 1 to it, and then I'm storing into address x. Okay, and this guy does exactly the same thing also. So now if I look at these instructions and those instructions, notice that unless I coordinate these two cores, these instructions could get done in any order at all. They could be interleaved in any order. So what happens if all of these instructions get done first and then all of those get done next? Do I get the right answer? I get the right answer. Of course, there are all the caches over there, but we said if you have coherent caches, they're transparent, you don't need to worry about it. So you can imagine that all of these loads and stores are going directly to memory, and you can immediately convince yourself that for this schedule, everything will work out fine. However, notice that these instructions could be interleaved in time in this order. So you do a load, an increment. Meanwhile, this guy does a load into his register, and then this guy does a store, this guy does his store, and you notice that X will have the final value of 4, because both of them have read the old value. Data race, big problem. We don't want this kind of non-determinism. There's good non-determinism if it results in Church-Rosser and all that nice diamond property and so on. This is evil, right? You don't want programs to behave this way. Okay, so what should I do?
Lock.
A lock, okay? But how are locks implemented? Okay, so this is a problem. It turns out there's a really interesting history behind it. So this kind of a problem with atomic updates, right? Read, modify, write. That's what it's called. I want to read a variable, do something with that value, and then write back to it. And I want that whole thing to appear to be instantaneous, right? So this problem first showed up in operating systems. And so people tried all kinds of tricky combinations of loads and stores, and well, if you do this load before that store and this and that and so on. And then there was a guy who came along and said, no, you guys are all crazy, right? This load, stores, all of this stuff, okay, we need that stuff, but what I'm going to do is I'm going to give you a small number of atomic instructions. These are read, modify, write instructions, which I'm going to guarantee in the hardware that they appear to execute instantaneously. And then any other atomicity that you want, updates and so on, you can build out of that. So I'm going to give you a primitive which does one of these atomic instructions. Everything else you can build out of that. Okay, so he cut the Gordian knot. You know that saying, cutting the Gordian knot? So he solved the problem by basically saying, you guys are solving the wrong problem, dudes. Here is the way to think about it. It's not some tricky combination of loads and stores to get this kind of atomicity. I'm going to give you a primitive atomic instruction in the instruction set. The hardware guarantees that. You can build everything out of that. Okay, so it's a name that you've heard before. And I know that because I mentioned his name during my lecture in the context of an algorithm. He got the Turing Award. He invented a graph algorithm. Okay, Dijkstra. Very good. All right. So, this was what Dijkstra told us, right? So it's a remarkable idea. Okay, so this is basically saying the same thing. So the architecture is going to provide a small number of atomic instructions which do a little bit of read, modify, write, and then you can build everything out of that. Okay, so the question is, what should these atomic instructions be? So here's a very simple one that I want you to look at. So this is a swap as a memory address and a register. And the result of this is the value in the memory address and in the register just gets swapped. So if the memory has 0 and the register has 1000, at the end of this, well, those two values just get flipped. So you can see there's a read, modify, write. You're reading from the memory, and then you're providing a new value which you want to write into the memory location also. So this is called a swap operation, like that. Now, once you get these simple atomic instructions, then it becomes very addictive, because then you say, oh, you know what? As long as I'm reading the value from this address, rather than just writing the contents of the register, let me add the contents of the register to this address and write it. So that's called an atomic add. So an atomic add, you specify a register and an address. The result of doing the atomic add is it appears as though the contents of the address were added to the contents of the register and written to this address instantaneously. Does that make sense? Okay. All modern ISAs have a zoo of atomic instructions. There are a whole bunch of them. You open up the Intel manual and it's a nightmare, right? Because they had to retrofit these atomic instructions back into the x86 instruction set, which was invented a long time ago. But basically, every processor supports a small collection of these atomic instructions, and I just want you to think about swap and atomic add. Just keep those two in mind. Any questions about this? Make sense? Yes? Compared to what? Well, This is giving you some additional functionality that you didn't have before, right? It depends on how you use them, depends on the program. So maybe what you're asking is how are they implemented?
Yes,
Okay, that's the next slide. So in fact, it turns out, given the cache coherence architecture that I showed you, it's actually very easy to implement swap, for example, or add. So let's take a look at that, and maybe that'll give you a sense of the overhead, okay? So hold that question, we'll come back to it. Oh, in fact, it's on the same slide. Easy to modify the messy protocol to implement an atomic instruction. Okay, so let's see whether we can figure out how to do a swap. So I'm a core, I'm going to do a swap operation. Swap operation has a register and a memory address. Let's say that address is not in my cache. So it misses in the cache, it goes out on the bus, and that cache line, ultimately the cache coherence protocol will stick it into my cache, right? And it will invalidate it from all the caches if it was there, because a swap is going to write. So it's like a write. So write invalidate, it's invalidated everywhere else. I have an exclusive copy of this particular line. Okay, once I have that, what should I do? How would I implement the swap? Update the so I read the value from that address. I read the address. Okay, I can do that. But what happens if, while I've read the value in that address, and before I do the swap, somebody else might steal that line, because you have these Snoopy caches going on. Oh, here's what I'm going to do. If I'm going to execute one of these atomic instructions, when I bring that address into my cache, I'm going to pin it in my cache. I'm going to just hold on to it and says, I don't care what address is on the bus. You can snoop. I don't really care. I'm holding on to this until my atomic instruction is done. And then you do the swap, and then you unpin it. And then after that, it gets stolen, right? And so a bunch of guys can all do their swaps, but notice that every swap gets done atomically. Obviously, you can do atomic add the same way. It's just instead of writing the contents of the register to the address, I'm going to do an addition, then write to this address, and then release it, unpin it from my cache. Okay, so now ask your question again. You said performance. What is the performance? Okay, so here's the short answer to your question. The short answer is uncontended atomic operations. If I'm the only guy who's doing this atomic operation, it's not any more expensive than a write. Because that's really what it is. It's just I happen to pin it while I do that computation and the write, but it's really just like a write. Good? Uncontended atomics are about as expensive as a write. If it's a contended atomic, what does that mean? Well, that means there are a whole bunch of guys all trying to do these atomic adds, for example. Well, then they get serialized, right? And that's where the serial bottleneck is. So then you have congestion in the sense that everybody, all of that gets sequentialized. And then that can be quite slow. So what you need to do is not so much avoid atomic operations. That's what a lot of people will tell you. Avoid atomics. No, you avoid contended atomics. So as long as there's not that much sharing, you're actually okay, right? So that's the answer to your question. Does that make sense? If there's no contention, nobody else cares about your atomic operation, that particular address, it's like a write. It's not any. Yeah? Nothing else writes to that address. That line, right? Yeah. But other caches could be writing to other lines in memory. I mean, that's okay, right? Okay. Good. All right. Now here's a limitation of atomic instructions. So if you think about this implementation that I told you for atomic instructions, you realize if you want to do an atomic read, modify, write on a piece of data that's larger than a cache line, well, then you're going to have a problem because, I can't quite pin down, a whole chunk of memory. So the way we handle that is these atomic instructions don't solve the atomicity problem for updates to large amounts of data. That, the implementation I'm going to show you, has to be handled at the software level, at the pthreads level, using locks or some other operation. Okay? So these atomic instructions just let you atomically do read, modify, writes to ints and floats and doubles and things like that. That's the way to think about them. And you can do a lot with that. Are we good? Okay. Well, we're ready to write some pthreads code. This was all at the ISA level, at the architecture level. And again, summarize the two main concerns. Cache coherence, and you have to worry about true sharing and false sharing. And the second is you need to use atomics to make sure that cores are synchronized properly. And at this point, you should have a mental model of how these things are actually implemented, because that gives you a sense of where the overheads are. Like, for example, the question that that gentleman asked, what's the overhead of an atomic? You think about the implementation, it's clear. Uncontained atomic is like a write. Okay? All right, good. Pthreads. Okay, so what's a thread? So pthreads is a library that we use in order to write programs for this kind of an architecture. We're going to assume cache coherence. We're going to assume that there is a zoo of atomic operations, and we're not going to worry about memory consistency. Okay, so a thread is basically a software analog of a core. So it has its own program counter, stack pointer, registers, stack. However, all the threads share the globals and they share the heap. So that's how they communicate with each other, by writing to globals, writing to heap. We're going to keep it simple. We'll just use globals for doing this communication. Okay, so threads are a software construct, cores are a hardware construct. Somehow you need to attach a thread to a core so that it can execute. So that's managed by the runtime system, or in some cases by the operating system. In the kinds of applications we're interested in, we're going to assume this. Number of threads is at most equal to the number of cores. I may have fewer threads, but it's never the case that I'm going to create a lot more threads than the number of cores that I have, because I'm going to use these threads in order to do some parallel programming. And if I don't have that many cores, then there's not much point in creating all of them, right? So I'm just going to assume that. But there are a lot of subtle issues about how this mapping is actually done. We're not going to worry about it. Okay, one little detail to understand some of this code that I'm going to show you. It turns out to be convenient in all of these threading libraries to think about threads as having two kinds of names, right? We're going to refer to these threads within the program by using two kinds of names, right? So the first name is the name that the pthreads library gives that thread when that thread is created. So as you'll see, there's a master thread that begins executing main, and there's a call that you can make to create a thread. So you're calling a pthread library routine. It doesn't matter what it does. When it comes back, it says, okay, I've created a thread, and here is an opaque handle. Here is a name for that thread. And if you ever want to query the pthreads library, for example, for the status of that thread, has that thread finished? Is it dead? How come I haven't heard from this guy in a while, right? Well, you have to use that opaque name because that's the only thing that the pthreads library understands. But that's a little like a social security number, right? It's like a canonical name for an individual. So in the US, at least when you're born, you basically, the government issues a social security number to you. And in any communication with the government, well, you have to use that social security number. But that's not very convenient for talking with each other, right? It's like, hello, 248-3297. Okay. So what do? Well, we give, you not only have a social security number, but you also have a first name, right, that we use. So the first name is essentially used within the application program to refer to a thread. If you're thread 0, I want you to execute this piece of code. So you can do that, but I want to use names like 0, 1, 2. So those are the short names, as I'm going to call them, usually an integer, and they're used by the application program to tell threads what to do and what parts of a data structure to read and so on. Okay, does it make sense? There's sort of a canonical name, which I have to use if I'm asking the pthreads library for the status of a thread and so on. Those are the opaque handles. But in the application program, I'm just going to use these short names. And there's a little bit of translation that needs to be done, and I'll show you that. Okay, so the program, we're going to assume there's a C program, there's a main. So program execution begins, there's a master thread, it begins executing main. And that thread can create, in fact, any thread can create a new thread by invoking pthreads create. Okay? Now, for those of you who are used to all of these wonderful type systems in Haskell and so on and so forth, if you start looking at the C type system, you're really going to throw up because there's all these void stars and all of that sort of thing. Okay, so we're not going to worry about what void star means and so on and so forth, but basically, here is what you need to know. When you create a thread, when you ask the pthreads library to create a thread, you also pass a function, right? And say, when you create that thread, let it start executing that particular function. That's the work that the thread is going to do. And since functions take parameters, you also pass a parameter. So these two arguments over here, it's basically you're passing the function and you're passing the parameter. So when that thread is created, it begins executing that function with that parameter. Okay? And then the pthreads library, after it's created that thread, will return that opaque handle to you. And I know it doesn't look like a return, looks like a parameter. Okay, this is all the stupidity of C. But basically, to create a thread, you use pthreads create, you specify the function and the argument. The thread is created, it begins execution that function with that argument, and then you get back this opaque handle that you can use in order to query the pthread system for the state of the thread. Okay, and what do you put in the argument? Well, typically it's a struct of some kind, so it's a record, and one of the things in that record is the short name that you're going to use. So you create, pthreads will create this thread and you say, oh, by the way, I'm going to refer your thread 0 or thread 1 in my program. And so you know what your name is, and then you can execute the appropriate code. It's exit. Okay, we don't worry about this. So here is your first pthreads program, and as you can see, it fits on a single line. Sorry, not a single line, a single slide. Okay, so there are some header files you have to include. There's some bookkeeping that you need to do, and I'll tell you about that in a minute. So here is the function that all the threads are going to execute. This is absolutely required. It's called a hello world program, as you know, and you have to start with a hello world program. So this guy prints hello. So this is the function that's executed by every thread. This is main. So the main thread, the master thread, execution begins over here. And as you can see, there's basically a loop over here. The loop executes for how many threads you want to create. That's just some constant I put in the program. And in each iteration, it basically prints something out saying creating thread 0, creating thread 1, creating thread 2. So I'm just using the short names over here in the print statement. And then what I'm going to do is call pthreads create with the print hello function, and then I also pass it the parameter. And this parameter is going to tell the thread what its short name is. So what I'm going to do is I create, and this is like an idiom that's used in all pthreads programs. In order to do this in a systematic way, you create an array that has as many elements as the number of threads you want to create. And then the main thread will populate that with the arguments that it wants to pass to each one of the threads. Okay? And then you also have another array just for keeping all the handles, these opaque handles. So notice what's going on over here, and there's a detail, you don't need to worry too much about it. Basically what I'm doing is going around the loop, creating a thread every time around, and then what I'm doing is passing it essentially what its short name is, so that it knows that. When I get that control back from pthreads, well, I've passed it this address over here, so the opaque handles are all stored in the handles array. Okay, and now what is the print hello thing doing? Again, this is a standard idiom from this parameter, doing a bunch of type coercions. Again, trust me, you don't want to know about this stuff. But basically, I extract out the short name for myself. I'm a thread. I'm going to begin executing this. I get my short name, and then I just say print, hello world using my short name. So print hello world from 1, hello world from 2, etc. And when I'm done, I just exit, and then this guy exits. So what is this program going to print? Sorry? Yeah, somebody used the right word. It's all going to be mixed up. Who said that? Oh, that was you. All right. So what is going to get mixed up? Yeah, before a thread is created, this guy is going to say creating thread, right? So creating thread 0, 1, 2, so those will occur in sequence. But after thread 0 has been created, it's just operating asynchronously from the master thread. Unless you do some synchronization, it just goes off and does its own thing. So you might get some output that looks like this. So create thread 0, thread 1, and then thread 0 says, hello world, I'm thread 0. Then thread 1 says, hello world, and right? So all of this gets mixed up. So that, it's a simple pthreads program. And now you've written your first pthreads program. And you can see how to, and that's a parallel program, right? Each of those threads will go to some core and start executing in parallel with each other. Questions? Okay, I'm going to make this a little more complicated now. Okay, so now we need to worry about synchronization. That simple program, threads just executed something and then died, right? But usually you want to synchronize, as we said. So pthread supports 3 kinds of synchronization constructs, and I'm just going to ignore barriers. I'm just going to focus on joins and locks. So what's a join? Well, this is a pthreads call that you can make in order to block yourself until some other thread terminates. So I want to wait for that guy to finish, and then I want to continue execution. So that's called a join. What is a lock? A lock is used to ensure mutual exclusion. So I want to solve this atomicity problem, but not at the level of an individual int or a float or something like that. There might be a big chunk of code that I want executed atomically. That's called a critical section. And so I want to make sure that only one thread is in this critical section. So one way to solve that x gets x plus 1 problem is I put that in the critical section, and then I can put a lock and unlock around it. And then the pthreads implementation will guarantee that all of this code gets done. Only one thread can be in the critical section at a time. And I can just put any arbitrary amount of code over there, and I get atomic execution for that. Yeah?
In the hardware, what's happening when we do lock?
Great question. Okay, so I'm going to show you that. Okay, so first let's do join. So this is very simple. So let's say there's a master thread. It creates this worker thread. There are a bunch of worker threads. They all do work. When they exit, well, what the master thread does after finishing the creation of all these threads is it can go and do a pthreads join. And it just does a join within a loop, so it can wait for any number of guys to complete. And when they're all completed, so you get the point of join? Okay, that's all. Okay, critical section in the code, as we said, is basically a bunch of instructions, commands, C statements, whatever you can put, and then you put a lock and an unlock around it. And again, pthreads provides 2 kinds of locks, which are called mutexes and spin locks. And basically you have to acquire a lock. So there are a bunch of threads, they all want to enter this critical section. Well, they all have to wait until they get the lock. So they try to acquire the lock. When they get the lock, they enter the critical section, finish their job, and when they exit, they release the lock, and then somebody else gets it, and so on. So the basic idea, I hope, is clear, right? Okay, so now let's dig in a little bit into your question. So how is a lock actually implemented? Well, basically a lock is just a variable with 2 states, 0 and 1. So 0 says available, 1 says not available. Let's assume that, right? And so that's really all there is to it. But for a mutex lock, there's also a queue that contains all of the threads that are waiting to acquire that lock. Because there could be multiple guys all trying to acquire that lock, and only one guy will get it, all the others get queued up at the lock. Okay? So here is how lock acquire happens. If the lock is available, pthreads will atomically change that to not available, and then it'll return control back to you. So you do an acquire, right? You do a lock, and then if that lock is available, control just comes back to you, and then you continue execution. If the lock is not available, what happens is your thread ID is put on that queue, and you just get stuck over there, right? In fact, you're under general anesthesia. You can't do anything at all because you're put to sleep until that lock becomes available. When that lock becomes available, well, then you're woken up by pthreads, and then you continue execution. So the invariant I want you to keep in mind for locks, mutex locks, is anytime you do a lock acquisition, you get stuck until that lock is given to you, and then you continue execution. Okay? All right. And lock release, well, basically you just say, I'm done. And then the pthreads implementation looks at the next guy in the queue, gives that guy a shot and says, wake up, wake up. Okay, and then okay, good. And here's the API. So there's a type for these mutexes. You have to initialize a lock, and you acquire a lock by saying what lock you want to acquire, and you release it by doing, so lock and unlock. Really, that's all there is to it. Nothing to it. Okay, now there's another kind of a lock which is called a spin lock. So a spin lock, again, is very much like a mutex, except that there are no queues. When you try to do a lock acquire, what happens is you get the status of that lock back. And you get to know, so if that lock is free, it's made not free, not available, and then you get a status flag back. You just get some value back saying, okay, you have it. Otherwise, it says, sorry, not available. And then you can go do whatever you want, and then you'll try later. again. So you don't get stuck if the lock is not available. You're just informed whether it's available or not. If it's not available, you're told that. If it is available, atomically, it's made not available, and then you're informed about it. That make sense? Okay. So can you implement spin locks using swap? Okay, so read this code out to me. So this is lock, and that's unlock. See how simple it is? Once you understand a few basic concepts, you can actually implement spin locks on your own. Okay, so tell me what this lock code is doing.
Trying to set that lock isn't not available.
It's doing a swap. So let's assume that the lock was free, right? So L had 0 in it. So what would this swap do? It would atomically write a 1 into it and it would give you the 0, right? And then you can return that 0. So if the return value is 0, it means you have that lock. And notice that the swap sets the variable to not available, right? The lock to not available, because you've atomically done that swap. You wrote a 1 into that location. So if anybody else does a swap after this, well, they see that it's not available. What happens if the value is 1? It looks like you wrote something into that G. Isn't that terrible? Somebody else had that lock, and you're writing into that lock variable. You're swapping 1 for 1. So, it doesn't do anything. It just stays at 1. When this guy, whoever has that lock, finishes, it's going to write a 0 to it. And then, of course, for a spin lock, this is why it's called a spin lock, you have to keep trying, and somebody will succeed. So that's it. That's how you implement spin locks. It turns out there's a better way to do it. This is called a test and set spin lock. There's something called a test and set spin lock. Lunchtime conversation. Okay, with that, let's put all these together. And I'm going to show you 3 programs. And they're all very simple programs. But it turns out their performance will be wildly different. And it's actually a very simple program. So it's basically just doing numerical integration. There's some function like this. And I'm sure you've seen this. You compute an approximation to the area under the curve by dividing some interval into small pieces. You evaluate the function at each value and then multiply it by h, which is the step size. So basically this integral then is replaced by a summation like this. And that'll give you some approximation to pi, which you can refine by reducing the step size and so on. So you've probably seen these sorts of things, okay? All right. And if you haven't seen it, basically that's the abstraction of what I'm trying to compute. Basically, I'm evaluating some function at a bunch of points and just adding up all of those values. It's a map reduce, right? So this is the map. I'm applying f to all the values of I between 1 and n. Those are the function evaluations, and then I'm summing them up. Okay, obviously the map can be done in parallel. Reduce can also be done in parallel if I assume addition is associative. It's not worthwhile doing that for shared memory machines because the number of cores is relatively small, as I told you. We're talking about 12, 20, 40 is the largest one that we have. So it's not really worth building that tree and so on that earlier you probably were told about how to do these reductions in parallel and so on. We're just going to do it sequentially. So we'll just exploit this map parallelism. Okay, that's the deal. Okay, so here is solution 1. So solution 1 is perhaps the most obvious one, and that is the following. So there's some big summation I want to do. What I'm going to do is the way I'm going to distribute the work is I'm going to create p threads, right? And then thread t is going to compute the values of this for t, t plus p, t plus 2p, and so on. So it's like a round robin way of assigning work. So if I'm thread 0, what are the what values of I am I going to compute with? 0, p, 2p, etc. And if you're 1, it's, okay, you get the idea. So this is one way of distributing the work, and so we'll just assume that's done. We're going to assume there's a global sum. There's a single variable called global sum. And the way that this p-threads program is going to work is you create all these threads, and then each thread basically is going to start computing its own contributions. And every time it contributes generates one of these contributions, it goes and adds that to global sum. Okay, very simple. Obviously, I need to have a mutex lock or something like that, because otherwise I get these race conditions, and we said, not allowed, shouldn't do that, bad. Okay. So, again, these slides have all the code in them, but here now I just want to show you the things to focus on. So here what I'm going to do is I'm going to have this global variable, It's a global variable in the C program, and I'm just going to call it global sum and initialize that to 0.0. And then there is this global sum lock. Notice it's a mutex. Okay? And here's the main program. So again, all of these have a common structure once you see how pthreads programs work. So this loop basically spins off all of those threads. And then notice it's just doing a join with each one. So when that loop completes, you know that all of the child threads have completed. And then you can just go ahead and print the value of global sum. Good? Okay, trivial. How about the function that's executed by each thread? So again, the first thing I do is, from this mess of types over here, which I really hate, you basically extract your ID. You extract your short name. Are you thread 1? Are you thread 0? Okay, what's your name? And then you just execute this for loop over here. You're computing the value in each iteration. I'm acquiring this lock. Then I update global sum, and then I do the unlock. Are we good? Okay, I know this is a C program and you guys probably hate it, but yeah, you can see what it's doing, right? Does it make sense? Okay, you think it'll perform well? Terribly. Okay, why will it perform terribly? Because you have all this lock and unlock. The lock and unlock is not too bad if the function evaluations take a very long time. If it's a very complicated function, well then it's okay. You spend all your time basically doing a function evaluation and then you go lock, update, and so on. Right? So it might work. For this function, that computation is so small that you're going to end up spending all your time waiting for this lock. So it's obviously a very stupid idea, but version 1, all right. So we need to improve this. So here's version 2. So in version 2, here's what I'm going to do. I'm going to say, look, the problem in the previous thing was I had all of this true sharing. There was one variable. Everybody was constantly updating that variable. What I'm going to do instead is I'm going to create an array, a global array, which I'm going to call sum. And sum 0, this is the location that's going to be used by thread 0 to do all of its summations. And thread 1 will do the summations here, thread 2 over here, and so on. When they're complete, then what we're going to do is return control to the master thread, and the master thread simply walks over this array, adds up the numbers in sequence, and gives you the value of pi. Does this make sense? So the first question is, do I need locks for this? Okay, why not? Yeah, each thread is basically assigned a different element of the array, and nobody else is reading or writing to it. So we're good, right? So I don't need the locks. Locks all go away. And I just accumulate in my element of the sum array, and then whenever I'm done. And then the master thread simply adds up all the numbers. So you understand the structure of this code? Okay, and you're already seeing what the performance problem here is going to be, which is fault sharing, right? So where is the fault sharing coming from? Well, if I have 3 threads, and let's say this guy has 3 elements over here, every time this guy computes a value, it wants to write to it, so it's going to invalidate it from here, and this line will ping pong here. This guy wants to write to it, well, that line will ping pong here. So basically, this thread will go ping ponging around all of your caches, and as I'll show you, your performance will really suck, right? Are we good? So it looked nice, right? It was like, oh, I got rid of all the locks, each guy is working on its own variable and so on, but actually I'll show you the performance is almost as bad as having a lock, right? Pretty sad. Okay, so here is the solution that actually will work well. So it's, sorry?
Use a GPU.
Use a GPU now. Okay, that might be a good idea too, but we're going to live with our Intel multi-core processor. So here's the basic idea, and it's very simple, right? What each thread does is, rather than immediately add its contribution every time it computes a value to, if I'm thread 0 to sum 0, right? I'm constantly updating that. I'm going to do all of those sums using a local variable within that thread. And only when I'm done, right, then I do just one write into this global array. And then I do a join with the master thread. And then everything else is similar. So you think that'll do well? Yeah? Okay. Is that the version you'd have written in the first place if I just gave you the pthreads constructs and said, go write a program for it?
Probably not.
The previous one? Yeah. Okay, so we've seen 3 versions, and just to summarize, the first one had true sharing. There was a single global variable and everybody was updating it, and you needed locks for that, okay? Now you could do that using an atomic add. So actually, since you're just working with a double over there, you can replace the lock and unlock with an atomic add. And all C compilers have what are called intrinsics. What's an intrinsic? Basically, yeah, it's basically, it looks like a C procedure call, except that the compiler knows that should be replaced with a particular instruction from that instruction set. So atomic add can be, it's an intrinsic, so it looks like you can call it directly from a C program. Okay, so you could write that version too. Will that perform well? You got rid of the locks, but there's still, yeah, you still have true sharing over there. Okay. The second version, you're summing into this sum array, so there are no locks. At some level, there's no contention, but there is false sharing. Okay, anytime I point to you, you have to say false sharing. All right. And then you have version 3. Version 3 does all the local summation, and then it just writes once into the global array. Okay, so which version does best? Okay, yeah, sure. All right, so here are some performance numbers. This was on a 40-core machine. This is a log scale. So this is 1 thread, this is 10 threads, and this is 40 threads. This is the time, so it's averaged over some number of runs, just to get rid of the noise. This is the one without any sharing, right? This was that third version that we wrote. And notice that it's scaling very well. In fact, you get perfect scaling. So this is wonderful. There's no sharing. Each guy is doing its own work, and then there's just a little bit of stuff that needs to be done at the end. We're good. This is a version with false sharing. This is the version you said you would have written. Sorry, doesn't perform well, right? There's no true sharing over there. That's the amazing thing, right? So why are you getting sucky performance here? You're getting terrible performance, right? I mean, it's hardly speeding up at all on 40 cores. So why is that happening? Because of false sharing. All right, very good. So you can see false sharing can really kill you, right? You're doing all these computations in parallel, but because of false sharing, you're dead, basically. And all you have to do is change a couple of lines in your program, and you got that false sharing version, and gee, you know, too bad. And these are the ones with true sharing. So what is the speed up? Oh, there's no speed up. Actually, there's a slowdown, right? There's a tremendous slowdown because basically everybody is sitting over there contending for that lock, right? And all of that happens in sequence. So there's actually much more work to be done in the parallel version than there is in just straightforward sequential version. That's this time over here. So the blue guy is basically the one with a lock, right? And you can see you're getting slowdowns because all the additions, lock acquires, etc., all of that has to be done sequentially. That's the whole point of a lock. Only one guy can have it at a time. And then these other 2 lines over here are showing you what happens if you replace that version with locks with atomic adds. Okay, and there are different versions of atomic add. This now has to do with that memory consistency model that we ignored. It turns out it doesn't really matter. And it doesn't matter because the problem is not with the lock. The problem is with the contention for these updates to that one variable. So it doesn't matter whether you do it with atomics. It doesn't matter whether you do it with locks. Ultimately, it's serialized. So this is, to circle back to your earlier question, right? So is there overhead? Well, okay, this is a contended atomic. Once you have a contended atomic, you're serializing things. Too bad. Okay? Okay, you look like you really want to ask a question, but no? Yeah. You're happy. Okay, that's getting too far. All right. Let's not, that's a stretch too far. All right. And this is for a smaller problem. Okay, I don't want to worry about that. Okay, so now we can summarize shared memory programming. And we've actually covered a lot of distance over here. I usually cover this in about 2 weeks in my undergrad course on parallel programming. And you guys, maybe it's because you're Haskell programmers, it's like we just went right through it. Cache coherence, atomic instructions, memory consistency models. That's at the hardware-software interface. You need to be, as a software programmer, you now understand why you need to worry about cache coherence. You need to understand how to use atomics properly. You understand the performance. Contended atomics are bad. Atomics that are not contended, cool. It's just like a write. Okay, and then I showed you the POSIX thread, the P threads, so POSIX threads, P threads, the API, how to create and destroy threads, and then I showed you joins, mutual exclusion, intrinsics, and we didn't do barrier. How do you get good performance? You basically have to minimize false and true sharing, right? And if you have critical sections, try and keep them small. So if you have to have critical sections, keep them small. But otherwise, if you can avoid sharing, much better. Okay? Zena, how much time do you have?
0.
Sorry? Minus 15. Is that right? Okay, so let me just quickly do distributed memory programming for you. So what are distributed memory programs? Well, basically, I have a bunch of machines like the ones that we've been talking about, right? And so I told you about the TAC Stampede cluster, so it's as big as that. Cartoon picture, latency numbers, basic MPI programming, the constructs that you have. Sorry? You want to see this cartoon? Lunch. Okay. Which is getting delayed, right? Okay, so basic MPI construct. You know what? Maybe I should I skip this? Or okay, give me 5 minutes and I'll finish this. Okay, so here's how you think about MPI. Essentially, there is no shared memory. You create a bunch of processes that communicate by sending and receiving messages. So it's a flat namespace for processes. There's some jargon, the rank. The rank is basically the short ID for a process. 0, 1, 2, 0 is always the master in this, okay? So when a program begins execution, it creates a bunch of these processes. MPI does that for you. You don't worry about it. And then control usually starts here, but all of them execute the same program, essentially. And then the master does a bunch of things and sends messages, and everybody gets going. So here are some constructs that are useful. How many processes are there in this world, right? How many are there? How many of us are there? The rank, it basically says, what's your short ID? What's your first name, right? Send, you basically have to say, so this is executed on one of these processors. You have to specify the variable that needs to be sent. The value of this variable is sent in a message to the receiver. You specify the rank. So if 1 wants to send a message to 2, the receiver rank will be 2, right? Because that's the ID of the receiver. And you can also send an entire array or an array with stride. And you have to do a receive, because sending just doesn't mean that this guy will do the get that value. So this guy has to do a send, this guy has to do a receive. It has to read that by doing this. Whatever value I'm going to get from this sender, please put that into var in my program. Right? Does that make sense now? Okay, this is what is sent, the value that is sent. This is, when I receive the value, write it into this variable in my program. Okay. As I said, this is called a single program, multiple data model. Everybody executes the same program, but you can do a branch depending on your rank to do different amounts of work, which is, of course, the point of all this. Hello world, hello. Okay. Collective communication. Here the idea is, in many programs, you want to do things like broadcast. So for example, maybe there's a parameter that's passed to the master, and then the master wants to give that to all of the other guys in this, all the other processes. So one way of doing that is it can do a loop with MPI send. So send to 1, send to 2, send to 3, and so on. But that's O of P, where P is the number of these processes. Now remember, over here, P is large. Right? We're talking about tens of thousands of these processes, unlike in the previous case. So we need to do this more efficiently than a linear time algorithm. So the way to do it is you actually create a tree of these processes. So this guy only sends it to 2 guys, and then these guys forward it, and so on. So in log time, you can essentially do the broadcast. And so MPI has a construct for this, so you don't need to worry about it. Basically, this is the variable that needs to be broadcast, and this is the guy who's going to do the broadcast. So this is the root. So the value of var, let's assume it's just the master. So that is sent to everybody. And whoever receives this value is going to write it into var, which is a local variable. Does it make sense? So this one construct specifies both what needs to be sent and where to store the received value at all the receivers. Good? Okay. All right, so this is a broadcast, and there's a similar thing for reductions. So in reductions, basically, every guy has some value, and they all need to be added up. and you can see numerical integration, okay, the same. We're going to need a reduction. Again, this is done using a tree, and then there is a call to MPI reduce. So again, that does the tree, etc., for you, and at the end of it, basically all of the values get added up. And now, since Zena is looking very unhappy, here is basically a sketch of a program that does that same numerical integration. So the basic thing to see is here is broadcast. What it does is it broadcasts the number of segments. This is basically that H, right? How many has to be done. So that's a parameter to the program, and it's broadcast from the master processor to everybody. Once you know what H is, so the function is just inlined over here, so you just compute your contribution in MyPy by just executing that loop over there. You're doing all of your summations, and then when you're done with your local sum, you execute MPI reduce, right? MPI reduce is a collective communication. That means all of the guys have to execute that MPI reduce. When all the processes are at that MPI reduce, then MPI takes over and performs that reduction for you, and that value appears in pi, right, in rank 0. And then if you're rank 0, you just print that value. Okay, I'm going very quickly over this, but I hope the basic idea is clear. The point-to-point, there's no shared memory. It's all distributed memory. So processes have to communicate by sending and receiving receive, and then you have collective communication. And the two most commonly used are broadcast and reduce. And with that, you can actually write your Pi program. Okay. Summary. Okay, so I've shown you low-level programming models for shared memory and distributed memory, so pthreads and MPI. And as you can see, it's really quite tedious. Trust me, all of those typecasts and so on with void star, you really don't want that stuff, right? You really don't want to write that stuff. But then that's the whole point of these higher level programming models. So if you have your parallel Haskell program, or in my case, a parallel Galois program, or whatever it is, the idea is those can be translated down into this level, and then all of the low level stuff of thread creation and et cetera, is all handled by these communication libraries or thread libraries. I, as the implementer of the Galois system, don't need to worry about all of these details, right? Because pthreads is already providing a lot of that functionality for us. We actually use the constructs in modern C++, which has all of these atomics and all that, but that's a different story. Okay, so what are the major problems? We're basically getting efficient implementation and then performance modeling, right? How do I get predictable performance? You change just a few lines in that pthreads program, and your version, your bad version, right? It just went like that. My version, yeah, okay. Few lines of difference, right? So that's the problem. Okay, so lots of work left for Stephanie's, and I hope I've convinced you that regardless of whether you want to do parallel Haskell or parallel Galois or parallel anything else, you need to understand something about the architecture, and I've given you essentially what you need to worry about in the architecture level, how to use atomics, what it means to have coherent caches, why you need them, false sharing, true sharing, etc., etc. Okay? So what I'm going to do in my next lecture is to basically show you how my programming model, this Galois programming model, could be implemented. So I'll give you some of the implementation details of what we do over there. Okay, there's time for 0 questions, but let's have 1 question anyway, if there is one. Or if you guys are ready for lunch, then we can all go for lunch and continue the discussion. Good.